Okay, this is the last section for our chapter 5 probability. This is going to be conditional probability and how to check whether events are independent or not. So first of all, to have conditional probability, it is if one event happens, then what's the probability of a second event happening knowing that the first event already has occurred? And it is denoted with this little straight line. This is read as the probability of event B given event A has happened. So this is read the probability of B given A. So this second one means that we know for sure that this has happened. This is now 100%. So knowing this has happened, what's the probability that this will occur? Okay, so in 2012, fans at Arizona Diamondbacks games would win 3 free tacos from Taco Bell if the Diamondbacks scored 6 or more runs. And in the season, they won 41 of their 81 home games and gave away free tacos in 30 of their 81 home games. In 26 of those games, they won and gave away free tacos. So we're going to let W denote winning a game and T denoting that the fans got free tacos. And then what's the probability if we chose a Diamondbacks home game at random? So first thing we want to do, because there are formulas we can use, but they're actually kind of confusing. So it's easier if you can just organize your information into a two-way table or a Venn diagram. So what do I know? I know for sure that they played 81 games. So that they won 41 of their 81 home games. So under 1 games, they won 41, and we know they played a total of 81, so I can figure out that they lost 40. I also know that they gave away free tacos. I know the total is 30. So again, if they played 81 games, if they gave free tacos away 30 times, they didn't give away free tacos 51 of those times. And then the third thing I know is in 26, they won and gave away. So they won and gave away free tacos 26. So I can now figure out that column, there were 4 times that they scored more than 6 runs, but they didn't win the game. They actually lost the game even though they had a lot of runs. And then I can also figure out, I can't figure it out this way, but I can figure it out this way. If this is 26 and this is 41, this has to be 15. Now I can fill it in either from the row or the column that number has to be 36. So I've arranged my information from what they gave me. And now I want to find the different probabilities. Again, please start using this notation and just writing, not just write down a number. Also, a lot of times I know you want to give decimals or percents, but always start with the original fraction. So I want to know the probability of winning or tacos. So winning a game, so I could follow my addition rule from last time, or means the addition rule. So what's the probability of winning plus the probability of getting a taco, but I want to subtract out winning and taco. That's the symbol for both events. That's an and. So the probability of winning was 41 out of 81. The probability of getting tacos was 30 out of 81, and I want to subtract out winning and taco, which was 26 out of 81, and I should end up at 45 out of 81. So it's perfectly fine to leave the fraction, but you can also change it to a decimal if you want. So if you did divide it out, it would be approximately 0.556. I would go 3 or 4 decimal places, or just leave it as a fraction. That's fine too. Now I used the actual rule from the formula sheet, but another thing that I do is winning or tacos. So I knew that there were 41 wins, and if I look at the tacos, I knew that I already used that 26, so winning 41, and then tacos that weren't won, so I actually just added 41 and 4 and went straight to my 45 that way. So that's why the table is nice. I can actually just count win taco and then just add up these three numbers to get my 45 out of 81. Now this is our given. What's the probability that they won given? Now again, there is a formula on the formula sheet that shows you what's the probability of W and T over the probability of T, but I don't really need to do that. I just figure out my new total. I know that they got a free taco. This is the given. I know they got a free taco, so now my denominator is an 81. I am now only interested in this column because they definitely got a free taco. So that's 30. And then how many of those did they win? 26. So I did not use that formula. I just used my table. When I have my given, I look at the given column, or sometimes it's the row, and that's my new denominator. So that's about 0.867 if you wanted to divide that. And then this is the other way. What's the probability they won a free taco given that they won? So given that they won, I am now only interested in this row. They definitely won the game, so my denominator is 41. And of those 41 games, how many times did they get a taco? 26. And that's really all there is to it. There is the formula sheet and the formula that you can use, but I think this is easier just to figure out your new denominator with those given statements, if you can. But again, it's all about organizing it into a table or a Venn diagram before you even start. Okay, so how can you tell if two events are independent? A mistake that I see a lot of students make here is they give me a logical reason of why they are, and basically if you can say that knowing the outcome of one event doesn't provide additional info about the next. For example, if I draw a card and then flip a coin, the card that I draw has no effect on the coin that I flip or die that I roll. So those would be independent events. But we can actually show it mathematically. So think about it this way. This is conditional A given B, and then this is just event A. Well, if they're independent, then B occurring has no effect on A, and they should be equal. You can also prove that A and B is just them multiplied together, but I think this is the one that goes. So are T and W independent? And explain. Well, we could say, I would think they're not independent, number one, because if they got a taco, then the team scored 6 or more runs, and can be a lot of runs in baseball. So if I know that they got a taco, I think it's more likely that they won the game. There's a good chance they won the game. So knowing that actually does give me some information about that. Or winning the game means they might have scored a lot of runs, so therefore I think they're more likely to get a taco. So I think we're going to find that they're not independent, but I can't just say what I just said. So I can actually use the information that I just did, and we already have a couple of these up here. So I could, and I'm just going to pick one, so I'm going to pick this one. So if they're independent, then the probability of getting tacos given that they won would be the same as just the probability of getting a taco. So I want to know if these are equal or not. So I already calculated this. This one was our 26 out of 41. And then what's the probability that they won a taco? The probability they won a taco was 30 out of 81. And you can look at the fractions and say they're not equal, or you could change them to the decimals. These two events are not equal, so they are not independent. So you can't just explain it away mathematically. You have to prove independence. Given working with a conditional probability should be the same as the probability occurring all on its own. If these were equal, then the fact that they won a game has no effect on whether they won or got tacos or not for free. Another mistake people make is they do this, but they don't answer the question. So you'd be surprised at how many people would get a partial on this because they showed this work, but then they, just because you put this doesn't mean you told the grader whether they were independent or not. So not independent, and it works both ways. You can say not independent and get partial credit because without showing the work, so just make sure you do both. Okay, this is not on the formula sheet, but the general multiplication rule is A and B is the probability of A times the probability of B given that A has already occurred. And if they are independent, this would just be the same as the probability of B. There is the conditional probability rule on the formula sheet, and you can transform it into this multiplication rule. Okay, so when is it better to use a tree diagram than a two-way table? Because sometimes with the information, you just can't get it all in a two-way table. So when we want to find the probabilities of more than one event. So this is an example of media usage and good grades. So how much time is spent on Facebook, Snapchat, all those things, and then grades. So they give us information. And again, I've already started the tree diagram. So we have students in a study. 17, so we have light media users. And it says 17% were light media users. So I'm going to put 17% on that column. 62% moderate, so that's 0.62, and 21 were classified as heavy. And I should verify that these should add up to 100%, because they didn't actually have to give me all. If they just gave me these two, I should know that this should add up to 100%. Of the light users, 74, so of the light users, 74%, so that's 0.74. And then 68% of moderate users described their grades as good, and 52% of heavy users. So again, I can figure out if 74% said good, then that means 26% said bad, because again, this should add up to one whole. Same thing with this one. The number that's missing here is 32%, and the number missing here is 48%. So then to calculate the probability, so the probability that they are a light user and good, I would just multiply those probabilities together. And that gives me 0.1258. And then light user and bad, 0.17 times 0.26, and that's 0.0442. And then a moderate and good, 0.62 times 0.68. Moderate and bad. Now I'm finding all the probabilities. You don't always have to find them all to answer the question. I'm just showing you how to do the table if you want to, because sometimes it helps to have it all then answer the question. And then heavy user and good. And then heavy user and bad. And then again, if you want to verify this, this should add up to one whole when you're done. So each row, that should add up to one whole. Each percentage here should add up to one whole. So now we'll answer some questions with this later. So I'll refer back to this, but we're going to use this in a later section. But that's how you can do a tree diagram. I don't know how you could really do that in a table as easily. So again, the multiplication rule for independent events, that little given shouldn't be there, is just the probability of A times the probability of B. Because again, if they are independent, then the probability of B would be equal to the probability of B given A. So if they are independent, I know that the probability of B is the same as the conditional probability that A has already occurred. So if they're independent, we just multiply them together. We talked about mutually exclusive before in the ORs. So what's the difference between mutually exclusive and independent? So I've got some scenarios here. If I select one card from a standard deck, and a lot of you don't know about cards, there's 52 cards in a deck, 26 of them are black and 26 of them are red, And then there's 4 suits. They have clubs and spades, which are both black, and they have hearts and diamonds, which are both red. So if the event A is drawing a red card, and event B is a club, well, clubs are black cards. So these would be mutually exclusive, because if I draw a card, it can't be red and a club at the same time. And then to prove, so they definitely are mutually exclusive or disjoint. The probability of A, so the probability of drawing a red card is 0.5. The probability of A given B, so this is saying what's the probability that I'll draw a red card given I know it's a club. If I know I have a club in my hand, I know for it's not red, so that probability would be 0. It's impossible. So since these two don't equal each other, they're not independent. So this is a case where it's not mutually exclusive and not independent. Another example, card is red, card is a 7. Well, there are 4 7s, 2 of them are red, 2 of them are black. So since there are 2 red 7s, they're not mutually exclusive. However, the card being red has a 1/2 chance, 0.5 chance, and the probability that it's red, or the probability that it's red given it's a 7, well, there are 4 7s, and 2 of them are red, so 2 out of the 4 is also 1/2. So this one came from 26 out of the 52 are red, and this is that 2 out of the 4 7s are red. They are both 1/2, so they are independent events. So knowing that I have a red card, a 7 in my hand, doesn't help me know what color it is. And then a third scenario, select one card. A, card is red. B, the card is a heart. All hearts are red. So since all hearts are red, they're not mutually exclusive because it's going to be red and a heart at the same time. The probability that it's red, again, is 26 out of 52, so it's 1/2. But what's the probability that it's red given that it's a heart? Well, there's 13 hearts and all 13 of them are red. So probability, it's guaranteed to be red if it's a heart. So again, that's not independent. And another thing that's helpful to know is if they're mutually exclusive, they can never be independent. Okay, so in baseball, we've got a baseball theme going on here. A perfect game is when a pitcher doesn't allow any hitters to reach the base in all 9 innings. It's very rare to happen, number one, because a lot of pitchers don't pitch all 9 innings. They might pitch 6 or 7, and then somebody goes in and relieves them. But if somebody's pitching a perfect game, they may keep them in there and let them try to reach it. So a perfect inning is where no hitters reach the base. That happens about 40% of the time. That's not so uncommon in a single inning that nobody gets on base. So to throw a perfect game, they have to have 9 perfect innings in a row. So what's the probability that a pitcher throws 9 perfect innings in a row? And this is what's important. We're going to assume that they're independent. So the probability of pitching a perfect game is the probability of the first inning perfect times the probability of the second inning perfect times all the way to the 9th inning perfect. So each one of these is 0.4. So 0.4 times 0.4. So basically it is 0.4 to the 9th power. So 0.4 to the 9th power ends up being 0.00026. So probability of pitching a perfect game is only about 0.026%. So again, what place value are we at? Tenths, hundreds, thousands, 100,000, tenths, hundreds, thousands, 10,000. So 26 out of every 10,000 games that's going to occur. So again, in the long run, 10,000 baseball games played, about 26 of them will result in a perfect game for the pitcher. Okay, first trimester screening. So there is a non-invasive test given during the first trimester of pregnancy to see if there's any abnormalities in the fetus. So according to a study in 2005, approximately 5% of normal pregnancies will receive a positive result. So that's known as a false positive. So even though the baby's perfectly normal, they're going to get a result that there is some abnormality in the chromosomes. And that's why you always get a second opinion, because the chances of it happening once, 5 out of every 100 women is going to get a false positive. But if you have a second test, the probability of getting a second false positive would be a lot more uncommon. So what's the probability there will be at least one false positive? Now I talked about the phrase at least one previously, so I'll show you why it's helpful to know it here. We're talking about 100 women. So if I want to know the probability of at least one false positive, so at least one false positive, I have to find the probability that there is exactly one. At least one, so I got to find the probability there's exactly one, plus the probability there's two, or I'm sorry, not plus, times the probability there are 3, all the way to all 100 get false positives. So again, very time consuming. You'd have to figure out each of those probabilities and multiply them all together. So we don't want to do that. We don't have time to do that. So what do I want you to remember when you see at least one? That's the same as 1 minus the probability of none. So no false positives. It's easier for me to just do 1 and the complement rather than do 1 to 100. So I know that if all 100 women, so the probability of none, if there's a 5% chance of a false positive, then 95% would not be positive, and that would be all 100 women. So the probability of none is 5% get a false positive, 95% get a correct result. So we would do 0.95 to the 100th power. So if I do 1 minus that, I'm going to get 0.9941. So the probability there's a 99% chance, over a 99% chance that one of those women, at least one of those women, is going to get a false positive. And that makes sense if 5 out of every 100 would get a false positive. So if I have 100 women, I would expect about 5 of them. So the probability that none of them is uncommon. So the probability at least one, I would think, is pretty likely to happen. But again, that's how I would show the work. Okay, on a recent day, the RJ forecast a 50% chance of rain in Summerlin and a 50% chance of rain up in Centennial. So I don't know if you know your areas around town. So what's the probability it will rain in both? Well, according to my rule, the probability of rain in Summerlin times the probability that it will rain in Centennial. Is it 0.5 times 0.5? So this is the probability of Summerlin and Centennial that it'll rain in both. So if I use this rule, I am assuming independence, but I don't see the word independent there. So does that mean that there's a 25% chance it will rain in both parts? So this is, the problem with this is I can't use that rule because they are not independent. Summerlin and Centennial Hills are close to each other. So what that means is if they're close to each other, then if it rains in, so if it rains in one area, it's more likely to rain in both. So in other words, if I know that it's raining in Summerlin, then that's going to change. That's not going to be 50% anymore. That's going to be higher, or vice versa. So it doesn't say that they are independent like it did up there in the pitching one. So because these are close to each other, they're not independents, because what I know about one affects the probability of the other. So I can't do that work like that. Okay, the conditional formula is on the formula sheet. So it's the probability of A given B. It's the probability of A and B occurring divided by the probability of B occurring. So when I asked earlier whether the multiplication formula was on the sheet, I said not really, but if you cross multiplied and solve this, so this can be transformed into the probability of A and B equals the probability of B times the probability of A given B. So this is the multiplication rule, but this is what's on the formula sheet, but it can be transformed from the conditional to the multiplication rule. Okay, so what's a very easy way to lose credit is not showing work. So you saw me write down the fractions, so make sure you show the fraction that gave you your decimal if you change it. So if you want to write your answer as a percent, make sure you show the fraction that got you there. Okay, so we're going to go back to our media and good grades. So we looked at the relationship and have all this written down already. So if you looked ahead, you already got it filled out. Okay, so what percent of students with good grades are heavy users of media? So what am I saying here? What do I know? They have good grades. So I'm finding what's the probability they are heavy users given they have good grades. So again, that's the probability of heavy users and good grades. I'm going to abbreviate even more. Divided by the probability of good grades. So the probability of a heavy user and good grades was this number right here. So heavy user and good grades is this 0.1092. Probability of good grades, all of these were good grades, so that's my denominator. So my denominator is the 0.1258 plus the 0.4216, and then I'm going to also include that 0.1092 again. So there were three categories of getting good grades. That's my denominator. My numerator is simply the heavy users with good grades. So if I figure all this out, it's going to end up being 0.1663. So knowing they get good grades, there's about a 16% chance that they are a heavy media user. So knowing that a student, again, this is the communicating part, gets good grades. So knowing that, the probability they are a heavy media user is about 16.63%. All right, last one here. So false positives and drug testing. So many employers require prospective employees to take a drug test. A positive result on this test means that they use illegal drugs. However, not all people who test positive actually use illegal drugs. Suppose 4% use drugs. The false positive rate is 5% and the false negative rate is 10%. So again, this is a case where I would probably go ahead and do the diagram. So again, I'm going to start off with my prospective employees. And the last example had 3 branches. This one is just going to have 2. They either use illegal drugs or they don't. And what did it tell me? It tells me that suppose 4% of the employees use drugs. So if 4% use drugs, that means 96% don't. And then they take a test and they either test positive or they test negative. Same thing here. If they don't use illegal drugs, they can still test positive or test negative. So they tell me the false positive rate is 5%. A false positive means they don't do drugs but still tested positive. So the don't use drugs testing positive is 5%, so that means 95% will test negative. And then the false negative rate, that means they use drugs but test negative, is 10%, so that means 90% test positive. So we want to know what percent test positive. So if I want to know the percent that test positive, it helps me to figure out what this is. So this is using and test positive. So again, I'm going to just multiply by branches. 0.04 times 0.9 gives me 0.036. Used and test negative, 0.04 times our 10%. Now again, these are small percentages because again, this is based on all employees. So they use and test positive. They should be testing positive if they use. The reason that's so small is because that's based on all the prospective employees, and not very many of them use drugs in the first place. So don't use and test positive. And then don't use and test negative. Again, I can verify this is a model that works because my percentages add up to one whole. So testing positive are these 2 groups. So testing positive. So again, if I have my tree diagram, all I have to show here is that I'm adding 0.036 plus 0.048, and that ends up being 0.084. So about 8.4% of these employees will test positive. What percent who test positive actually use drugs? So I know that they tested positive. So this is the probability that they use given they tested positive. So again, that's the probability of use and test positive over the probability of testing positive. So we already got our denominator in the previous question. So the probability that they test positive was our 0.084. And then the probability that they use and test positive. So again, use and test positive is just this group right here. So that's our 0.036. And that ends up being 0.429. So knowing that they tested positive, about 43% of them actually use drugs. So so that doesn't seem too good for the company, as far as if I were an employee that didn't use drugs, there's a pretty good chance that I'm going to test positive. So again, that's a case where you want a second test, because to get a false positive or a false negative twice in a row would be uncommon. But that's how you figure out these probabilities. So either with a two-way table, a Venn diagram, or in some cases like this, the diagram, the tree diagram, is beneficial. And that finishes up our probabilities lesson 5.3.